Hi, I'm Yichin Chen. I'm here to present our paper, Retraining-Free Merging of Sparse MoE via Hierarchical Clustering. It's an efficient and effective technique to reduce MoE models' memory consumption. To begin with, let's start from the MoE architecture. The input tokens will first fit into a router network. This router will decide the expert networks of the specific tokens to route in. After each expert produces output representations, it will then multiply with the corresponding router score and sum up to get the final layer output. This architecture shows superior performance than its dense model counterpart by activating only part of its parameters while inferencing. However, MoE models still suffer from the huge memory consumption. There are two categories of compressing MoE. The pruning-based method will directly remove expert networks and its router part, which lose the pruned expert knowledge entirely. Although there is a previous method that is zero-shot, retraining-free, and task-agnostic, it is not scalable to MoE with large number of experts. Another one is merging-based. It will first group the expert into clusters. After merging it, we can reuse the router by assigning the router score to the new group that original expert belongs to. Nonetheless, the previous work needs fine-tuning for each downstream task after merging expert. Therefore, we want to design a compression algorithm that contains both of the advantage of these SOTA methods. Let's dive deeper to get some clues. For pruning-based method, it iteratively searches all possible combinations of expert to minimize output deviation from the original model layer by layer. This gave us the clue that minimized expert output discrepancy would be the way of retaining the ability of original model. On the other hand, merging-based method will group non-dominant expert to dominant one by similarity matrix, then use frequency-weighted merge. We eliminate the choice of dominant expert because the criteria they use is task-specific. Instead, we can achieve similar grouping by clustering methods. Here comes to our methodology of HC-SMoE. By defining the layer output, the approximation error between original model and HC-SMoE will be bounded by this equation by applying Jensen's inequality. And the study has showed that in the worst case, hierarchical clustering guarantees the solution will not exceed 3 times of optimum upper bound. Therefore, we use HC to be our clustering method. In order to apply HC on the expert network grouping, let's assume this is an embedding space of expert. At first, HC will view each expert as one cluster and group 2 clusters that are closer to each other, iteratively. For cluster distance definition, we use the average of all the paired distance within 2 clusters. We can set a target number of cluster R, and HC will iteratively update the cluster relationship until the number meets the target. There are many ways to define the cluster distance in HC, as well as the metric used to compute this distance. Here, we did a simple experiment to check all the combinations. D means the Euclidean distance between expert I and J, and the small e may represent the router logits, the weight parameter, or the output of corresponding expert, and we found out that the combination of using expert output and average linkage will give us the best performance. For the evaluation on zero-shot comparison among 4 baselines and 8 benchmarks, HC-SMoE achieves the best score among all settings for both Qwen and MoE and Mixtral. In ablation study, we showed that once a high-quality cluster is identified, the specific merging method becomes modestly influential on the final performance. To sum up, we propose HC-SMoE, a retraining-free, task-agnostic, and scalable MoE compression strategy with hierarchical clustering. For more details on the experiment and the method, please scan the QR code below. Thank you.